Today we'll be discussing logarithmic functions. To solve exponential equations, we need an inverse operation, just like adding and subtracting our inverses and multiplying and dividing our inverses. A logarithm is the exponent to which a specific base is raised to obtain a given value. In other words, it's the inverse of an exponential equation. It's possible to switch back and forth from exponential form to logarithmic form using the formula below. I really like this graphic because I think that it makes all of the variables different colors, and so it makes it very clear to understand where things go. So on the left we have b to the x power equals a, and on the right the log base b of a is x. So b is the base in both problems, so it's sitting on the ground on the left, and on the bottom it's a subscript. And then your a is on the right for the first one, and it's going to be with your logarithm, and then your x is your exponent, which goes by itself in the logarithm. And we'll do some practicing switching from one to the other in the next few examples.
Here we want to write the log of base 2 of 512 equals 9 in exponential form. You don't need to write them color-coded in your notes, but just for this example, I'm going to go ahead and write them in these colors so that we can follow along more easily. So we have log base 2 of 512, and that's equal to 9, which we're going to make pink because that's our x. So now we can go ahead and follow our pattern up here in the right, and we have our base, which is the green, which is 2, to the x power, which is our pink, which is 9, is equal to our a, which is 512, the blue, and that's our answer. We're writing it in exponential form, and we get 2 to the 9th is 512. Okay, here we're going to write log base 4 of 1 over 16 equals negative 2 in exponential form. Again, I went ahead and wrote everything color-coded, so we have log base 4 of 1 over 16 equals negative 2, and the colors match our rules up to the right. So now we're going to rewrite it in exponential form. We take the base of 4, raise it to the exponent of negative 2, and that's equal to 1 over 16, and we can double check that. We know that if we have a negative exponent, that puts it in the denominator of our fraction, and 1 over 4 squared is the same as 1 over 16. So writing it in exponential form, our correct answer is 4 to the negative 2 equal to 1 over 16. For this problem, we're going to go the opposite way. We're going to write 9 squared equals 81 in logarithmic form. So in order to write this in the colors, we want our base to be 9, our exponent is 2, and that's equal to our a, which is 81. Okay, so now that we have our colors all set up, we can go ahead and write it in logarithmic form. We have log of our base 9 of 81, our a, is equal to 2, which is our exponent. So the answer to write 9 squared equals 81 in logarithmic form is log base 9 of 81 is equal to 2.
This table shows two of the most helpful rules of logs. We'll be using these to solve exponential equations. The log base b of b is always 1, because b to the first power is b. Now, the second rule is that the log base b of 1 is 0, because anything to the 0 power is 1. So anytime you have the log of 1, no matter what the base is, it will always equal 0. We also have something called a common logarithm. If no base is written for a logarithm, the base is assumed to be 10. For example, log of 5 is log base 10 of 5. On your calculator, you have a log button that does not have a number with it. On your calculator, the button is log base 10. so you always want to make sure that when you are typing things in, you're using a base 10 log if you're using your calculator.
Now we're going to try evaluating some logs using mental math. Remember that log with the common base is 10, so this is log of base 10 of 0.01. When we don't have the log written, it's log base 10. So we don't know what this is equal to. So let's rewrite it in exponential notation. If we rewrite it using our rules, our base b goes down on the bottom, so we have 10. Our exponent comes from this side, so we get 10 to the x is equal to our a, which is 0.01. Now, if we read our decimal, this is 1/100th. So if we think of that as a fraction, 1/100th, now we can think about what our exponent is using mental math. Well, 100 is 10 squared, but it's in the denominator, so our x is going to be -2. So x to the -2 power is 1 over 100. So using mental math, we were able to evaluate the log of 0.01. The log of 0.01 is just equal to -2. How about the log base 5 of 1/5? Again, we're going to set this equal to x, rewrite 5 to the x equals our a, which is 1/5. Now here we just have the 5 in the denominator of the fraction. To move something to the denominator of the fraction, we just give it a negative exponent. So x is -1. 5 to the -1 is 1/5. So the log base 5 of 1/5 is -1. Now let's try evaluating log base 5 of 125. We already have our base written, so our base is 5. We'll set this equal to x. Our base is 5. We don't know what the exponent is, and it's equal to 125. Okay, so now we have to figure out what our exponent is. We can try 5 to the first. 5 to the first is 5. So it's not going to be 1. 5 squared is 25, so it's not going to be 2. 5 to the third is 25 times 5, which is 125. So our exponent, our x, is 3. So the log base 5 of 125 is equal to 3. Here we're going to evaluate the log of 0.00001 using mental math. So we have log, common logarithm, so base 10 of 0.00001 is equal to something that we don't know. So we rewrite it. 10 is our base to the x power equals 0.00001. Now we can rewrite this one as a fraction. 10x is equal to 1 over 1, 2, 3. 100,000. So we have tenths, hundreds, thousands, 10,000s, 100,000s. Now 10 to the x, this is going to be, the x will be negative, and there are 5 zeros, so it's going to be -5. The negative puts it in the denominator of the fraction, and 10 to the 5th is 10,000. So log of 0.00001 is -5.